Metrology, the science of measurement and quantitative comparison, is one of the most fascinating and fundamental areas of science. It's in the background, behind the scenes, but without it, nothing would work. Metrology is the source of all the units and scales that we use to measure the world around us. With the help of the Open University and the National Physical Laboratory, these short programs examine the 7 SI base units from which all other units can be derived. The kilogram, the meter, the mole, the second, the Kelvin, the ampere, and, in this episode, the Candela.
The candela is the luminous intensity in a given direction of a source that emits monochromatic radiation of frequency 540 times 10 to the 12 Hertz, and that has a radiant intensity in that direction of 1 over 683 watts per steradian. The candela is a measure of luminous intensity, and that's effectively a way of measuring how good a light source is at allowing us to see. It's unique amongst the SI base units because it's the only one that does bring in this idea of human perception. It needs to be a measure that relates to how we actually see things. And it's important to remember that vision is subjective. So the way that we see things is different to, say, a snake or a bee. They've evolved to see different portions of the spectrum, whereas we see best in a very specific region, which is the region that we call the visible. Let's have a look at the electromagnetic spectrum. It goes through from gamma rays right the way up to radio waves. The region where we see best is this central portion, what we call the visible. Now, if we were to have the same vision as a snake, for example, we'd see better towards the infrared region up here. Bees, on the other hand, see better in the ultraviolet down in this region. But this central region is where human vision is most effective. And what we want from the candela is a unit that allows us to measure that radiation that's in the visible region. Now, the simplest way to do that would be to simply add up all the radiation that we've got there. That would be what we call the radiant intensity, and that's measured in watts per steradian. The problem is that that doesn't tell us how effective that light is at stimulating vision. It doesn't tell us how luminous it is. And that's what we need from the definition of the candela, this idea of luminous intensity rather than radiant intensity. It's important to bring in that idea of the human eye response, because when we look at the definition, it's actually just for one wavelength and one radiant intensity. If we're measuring a real light source like these, we need to know how the eye responds at different wavelengths. Let's bring back the electromagnetic spectrum now and have a look in more detail at what happens in the visible portion of the spectrum and precisely how the eye response changes as we go through the visible. So if I was to plot the average human eye response, it would start down here in the blue. It's sort of zero as you go through into the ultraviolet. It comes up, comes down, and it tails off again through the red into the infrared. And actually, the equipment that we have in this lab here, we use to calibrate instruments that are designed to match very precisely that human eye response curve. So if we look at the peak of the curve here, that corresponds to a frequency of 540 times 10 to the 12 Hertz. And that's what we use in the definition of the candela. It's actually the peak of the human eye response curve. So why do we have the factor of 1 over 683 watts per steradian as part of the definition of the candela? To understand that, we have to go right back to the original definition, which was in terms of candle. It was actually a particularly special candle. It was made of a particular type of wax. But it was defined that the luminous intensity of that candle was 1 candela, and that's where the name comes from. So over time, this rather unstable source was replaced by better sources, things like gas lamps and tungsten lamps. And eventually, in about 1940, it was replaced by something called a Blackbody, and that's actually what we have here. So what exactly is a Blackbody? It's essentially a cavity, a specially designed cavity, that's enclosed in a furnace. And the cavity is designed so that it's a perfect absorber of radiation. But that means that as you heat it up, it's also a perfect emitter of radiation. And the amount of radiation that it emits at any wavelength depends just on its temperature. So that means that as long as you know what its temperature is, you can very precisely calculate exactly how much radiation it's giving out, and therefore how much light it's giving out, how much visible radiation it's giving out. So that's why we have the factor of 1 over 683 watts per steradian. It's to make sure that with all of the changes that have happened in terms of the definition, moving from a candle through gas lamps, through tungsten lamps to a Blackbody, and ultimately to our new definition, that one burning candle now still has a luminous intensity of 1 candela.